we were talking about section 2.8, higher derivatives. Now we know that the derivative of a function is itself is a function. And since it is a function, we can take the derivative of that function. So what we're doing is taking the derivative of a derivative. The result is a function called the second derivative of f, and is denoted with f double prime here. We see these two slash marks. Those are the prime notation. So if y equals f of x and we use Leibniz notation, then the second derivative of f of x can be denoted as d of dx of dy dx. So what we're saying is the derivative of the derivative. We can abbreviate this as using a d with a superscript 2 and a y, and with respect to x with a superscript 2. Now, if we use this capital D notation, that symbol being the operator, the differential operator of d with a superscript 2, it indicates that the operation of the differentiation, or we're taking the derivative twice. So we have these following notations here. We have y double prime. We could say f double prime of x. We could say d, it looks like it's squared. So let's just call it d squared y over dx squared. Or we can say capital D squared of f of x, or d squared with a subscript x, because it's with respect to x of f of x. So we have all these notations. So we have like the Lagrange's notation, we have Leibniz notation. And so anyways, let's take a look at example 1. We have, it's asking us to find the d squared y of dx squared if y equals x to the 6. Now we notice with the superscript 2, we'll notice that we are taking the second derivative of x to the 6. So let's take the first one. So dy dx using Leibniz notation is equal to, take the exponent down, and then it's just subtract 1 from the exponent here. So we have 6x to the 5. Now, if we were taking that's the first derivative, we have to take the second derivative. So the second derivative of y with respect to x is d of dx of that first derivative. So really what we're saying is we're taking d of dx of 6x to the 5. So treating this as a function and taking the derivative of that, we say, okay, we have a constant 6, but it's going to be multiplied by this 5 because that by the power rule of derivatives, it's going to come down. So 5 times 6 is going to be 30, and we have x. And of course, this exponent will be brought down by 1. So we have 30x to the 4. All right, taking a look at example 2, we can find the second derivative of f of x if f of x equals 5x squared plus the square root of x. We don't like the square root of x written this way, so we're going to rewrite it with a rational exponent. We know that the square root of x is equivalent to saying x to the 1/2. And now we can use a power rule here along with the constant rule. We have a constant out in front, multiplied by this is going to come down. 2 times 5 is 10. Bring the exponent down by 1. And then here we have the exponent down, so 1/2 x, and then half minus 1 is going to be negative 1/2. Okay, so here is the first derivative of the function. If we're taking a look at the second derivative of the function, we can treat this as as the original function and take the derivative of that. So the derivative of 10x is 10. And then we have our half as constant. Bring down the exponent, so that's going to be negative 1/2. And then it's going to be x. Negative 1/2 minus 1 is negative 3/2. And here we can say that we have a 10 plus half times a negative 1/2 x to the 3/2. So we can say that that is equal to 10 plus, let's combine this. Oops, not a plus. We'll make that a negative. So minus 2 times 2 is 4. So that's 1/4 x to the negative 3/2. All right, let's tackle example number 3. We're asked to find the second derivative. Oh, and using the x value equal to 1 if f of x is originally 2 minus x squared, all in brackets, to the exponent 10. Now, we're going to have to use the chain rule here because we have a composite function of some function that is raised to the exponent 10. So let's see. Let's take the first derivative of this function, f prime of x. We'll use Lagrange's notation here, and then we'll say, okay, by chain rule, the exponent is going to come down. We have 2 minus x squared as a bracket. That doesn't change, but then this exponent is brought down by 1. Now, by the chain rule, we multiply by the derivative inside the bracket. So taking a look just inside the bracket, we have 2 minus x squared. The derivative of that is, of course, the derivative of a constant is 0. And we have this negative. The 2 is going to come down. So we have negative 2 and then x to the 1. So we don't have to write the 1 here, but there it is. By the chain rule, that is the first derivative. And let's just combine that and say, okay, 10 times negative 2x is going to be negative 20x, and then multiply by 2 minus x squared to the exponent 9. Okay, now let's tackle the second derivative. So second derivative has 2 primes here, this f double prime of x. And now we have, it looks like one function here multiplied by another function, and there is a composite function here because it's a simple function raised to the power 9. So we're going to have to use the power rule. So let's keep the first one the same. So negative 20x, and then the derivative of this composite function. So that is going to have a 9 in front. It's 2 minus x squared. That doesn't change, but this exponent comes down by 1. So that's going to be 8. And then multiplied by the derivative of the inside of the bracket, which is going to be negative 2x. Okay, so we can close that off. And now by the product rule, it means that we have to keep the other side the same. So this is 2 minus x squared to the 9, and then multiplied by the derivative of this function, which is negative 20. Okay, so I wonder if we can simplify this a little bit here. So this is going to be, negative 20 times 9. This is going to be, what's negative 20 times 9? Negative 180. Oh, also this multiplied by this 2. So 2 times 9 is 18. 18 times 2 is 36. So we actually have, with this negative, this is going to be actually 360. We have x, and this x is going to be x squared. And then we have our 2 minus x squared to the 8. And then we have also added to this, actually it's going to be minus. So let's just make that minus. Minus 20 times 2 minus x squared to the 9. Well, we can continue simplifying here, but we were asked to find the second derivative evaluated at x equals 1. So in fact, if we were to keep going and say, well, f double prime with the x value being 1, we can actually just put the number 1 in for each of these x's. So 360, replace this x with a 1, that's squared. 2 minus, replace this x with a 1, that's squared, and then it's raised to the exponent 8, minus 20 times 2 minus 1 squared, and then the exponent 9. So when we do this, what is this going to be? Well, 2 minus 1 is 1. Well, 1 squared is 1. 2 minus 1 is 1. 1 to the exponent 8 is 1. So really we have 360 times 1 squared, which is 1, times 1, and then minus 20 times, well, 1 squared is 1, 2 minus 1 is 1, and 1 to the exponent 9 is 1. So that's just 1. So really we have 360 minus 20, which is 340. So that tells us then, if we have a value for x, we may not have to simplify completely until we can find our final answer. We can use that x value to plug in for x before having to simplify all the way. All right, well, the first derivative of a function can be interpreted as either the slope of a tangent line or a rate of change. The second derivative then can be interpreted as the rate of change of that rate of change, or in other words, the rate of change of the slope of the tangent line. Now, we'll learn more about this, but if you think about even in physics, we think, okay, if we have a distance function or a displacement function, then the slope of that distance function, if we're talking about with respect to time, would be the speed function, how fast we're going. Now, if we took the rate of change of the speed, then how is speed changing or velocity changing with respect to time, then we're talking about acceleration. How fast are we changing speed, or how slow are we changing speed? Now, if we take a look at the derivative of that, actually, we're talking about the third derivative now. Then the third derivative of the distance function would be how fast are we accelerating? So in physics, they may call that jerk, right? If you ever like accelerated really fast, you feel that jerk. Anyways, that's kind of a real world application to a third derivative, making sense of, you have a distance function, you have your how the distance changes over time, that's speed. How the speed changes over time is acceleration, and how fast or slow you're accelerating is we can call the jerk. So we have these other notations here: third derivative, y triple prime, f triple prime of x, using the superscript 3 in the Leibniz notation, or the operator. Now, beyond the third derivative, we don't usually use the prime notation. So if we just have the fourth derivative, then we would just use f and then a superscript, but in brackets, the number 4, instead of using like 4 quadruple prime. So if we're talking about the nth derivative, then we have y superscript with a bracket n of x, f with a bracket n in the superscript, and then here like an exponent, a d to the n, or d to the capital D to the n. And sometimes you'll have this subscript x to show you that it's with respect to x. Let's look at example 4. It's saying find the first 5 derivatives of y equals x to the 4 plus 2x cubed minus 5x squared plus 3x minus 6. All right, we have a nice polynomial here. It's continuous and differentiable everywhere. So let's take the first derivative. So if we take the first derivative, we'll denote it as Lagrange's notation here. So y prime is equal to, we know we can treat the derivative of this polynomial with the derivative of each of the terms and use the power rule in each case. So we have x to the 4th, derivative of that is going to be 4x cubed. Remember, bring the exponent down and then drop the exponent by 1 here. So we have plus the derivative of 2x cubed is going to be 6x squared, minus the derivative of 5x squared. Remember, this constant 5 can wait and then multiply by 2. So this is going to be 10. Bring the exponent down by 1. So that's x. And then plus 3. X to the 1 will go down to x to the 0, which of course is just 1. And of course, the derivative of a constant is equal to 0. So we have the first derivative. We can treat this now as a function and say, okay, the second derivative is going to be equal to 4 times 3, so that's going to be 12x squared plus 6 times 2 is 12x, and minus 10. Now this is x to the 1, so it's going to go down to x to the 0, and of course the derivative of a constant is equal to 0. So that's the second derivative. Treat this as its own function, and now take the derivative, the third derivative, the derivative of this second derivative, it will become the third derivative of the original function. So 12 times 2, that is 24. Bring the exponent down by 1, so that's x to the 1, and then plus 12. Okay, so the fourth derivative, denoted here with a bracket 4. The derivative of 24x is 24. The derivative of a constant is equal to 0. So we have the fourth derivative, and now the fifth derivative is the derivative of 24, but the derivative of a constant is equal to 0. So we have the fifth derivative, and we have the first 5 derivatives of this original polynomial function. All right, I think we're ready to tackle example number 5. So example number 5 says we have an original function here, x cubed plus y cubed is equal to 5. And it actually gives us a hint. It says use implicit differentiation to find y double prime. Now, of course, to find y double prime, we'll probably have to get the first derivative. And remember that y is a function of x as well. So we're going to have to use implicit differentiation just to find the first derivative. So let's take the derivative of both sides. The derivative of x cubed is 3x squared. The derivative of y cubed, remember that y is a function of x, so we're going to have to use the chain rule. And so we have 3y squared multiplied by y prime. Now, of course, if you were using Leibniz notation, then y prime could be denoted as dy dx. And then so we'll always go back and forth between the notations. Of course, the derivative of a constant is equal to 0. Now, to find the first derivative, then we would isolate this y prime, or the dy dx. And if we do that here, let's see if we say, okay, if we subtract 3x squared from both sides, then we'll have 3y squared y prime is equal to negative 3x squared. And of course, then it's just to divide by 3y squared on both sides. So we'll have y prime is equal to negative 3x squared over 3y squared. But of course, we have a common factor of 3 in the top and the bottom. So this simplifies to negative x squared over y squared. So we have an expression for the first derivative, which is y prime is equal to negative x squared over y squared. Now we have to find the second derivative. So let's just rewrite this. We'll say y prime is equal to negative x squared over y squared. Oops. All right, so we might have to return to this later, but let's take a look at y double prime. Now remember, we have a function divided by another function, and we know that when we're taking the derivative of a quotient of functions, then that's going to be equal to this formula that we derived, is that g on the bottom is going to be squared on the bottom, then it's going to be g times the top derivative minus the top times the bottom derivative. Okay, so using that, then we have y double prime will be equal to, let's take the negative out. So what we're doing is we can say that the y double prime will be equal to negative the d of dx of y prime. Actually, not negative. So this is going to be x squared over y squared. So what we're doing is just taking the negative out. So we have negative, and then using the formula of the quotient rule, the y squared is going to be squared on the bottom. So y squared squared is going to be y to the 4. Now we have the y squared, and the derivative of x squared is equal to 2x. And then we subtract, keeping the top the same, x squared, and then the derivative of the bottom. Remember, by chain rule, it's going to be 2y and then multiplied by y prime. All right, so let's continue to simplify here. This is going to be equal to 2xy squared minus, we'll just put the 2 in front here, so 2x squared y prime over y to the 4. Okay, now this negative out in front, I kind of like having a bracket out here, so I just make this a bracket. Okay, remember that we had an expression for y prime. If we look up here, we notice that y prime is equal to negative x squared over y squared. So in fact, we can actually put that expression in for y prime. So this, maybe we'll just make it, so right here, this piece is, this is just going to go in for that piece there. All right, with that in mind, then we have, substituting everything in, we're going to have, I like having the bracket out here, we have 2xy squared minus, I'm going to start this on the top, 2x squared y, and this is going to be multiplied by negative x squared over y squared. And of course, all of this is over y to the 4. And then we'll close off this big bracket. All right, with that in mind, we have, I'll just make it a compound fraction here. I do like having these square brackets on the outside. So we have 2x y squared minus, let's go, oh, this minus and this minus are going to combine. That's going to be a positive, and we'll still have the 2 x squared, and x squared will become x to the 4, and then it's going to be y over y squared. And of course, all of this is going to be over y to the 4. All right, keeping that square bracket there, we actually can simplify this y over y squared. Y over y squared just simplifies into 1 over y. So we have our 2xy squared plus 2x to the 4 all over y, and this compounded over y to the 4. Now, of course, we have two terms here. One has a denominator, the other one has a denominator of 1, but we can combine that. Let's do that over here on the side. So we have 2xy squared. Let's get a common denominator of y. So what we're going to do is multiply by y and also divide by y. A clever multiplication by 1 here. So then we have plus 2x to the 4 over y, but now these have the common denominator of y. So we can actually combine this. So y squared times y is going to be 2xy cubed over y plus 2x to the 4 over y. And this can be combined now into 2xy cubed plus 2x to the 4 all over that same y. So we have 2xy cubed plus 2x to the 4 all over y, but that is all over y to the 4. Now, one of the things that we know of when we take a fraction and we're dividing by another fraction, really this is just 2xy cubed plus 2x to the 4 over y multiplied by the reciprocal of y to the 4, which is 1 over y to the 4. And notice now the bottom is just going to be y times y to the 4. So if we rewrite this, then this is going to be equal to, you still have the negative in front, you still have this big bracket, and you have 2xy cubed plus 2x to the 4 all over now y to the 5. All right, we can even simplify this more because we have a common factor of 2 and a common factor of x. So if we bring that all the way out, we can say this is minus. Actually, we can even put it outside here with the negative. So 2x. And then this is going to be multiplied by, you still have y cubed plus, remember that if you take one x away, it's going to be x cubed. And then we have y to the 5. Now, this y cubed plus x cubed is actually pretty special. In fact, we know that addition is commutative, so y cubed plus x cubed is equal to just x cubed plus y cubed. And if we just write it like this, we might be able to recognize something. So 2x times x cubed plus y cubed all over y to the 5. In fact, if you take a look at the very original part of the question, remember here we see that x cubed plus y cubed was equal to 5. So wherever we see x cubed plus y cubed, we can just replace it with 5. Well, that's brilliant. So we can change this x cubed plus y cubed into 5. And here you can see it, x cubed plus y cubed is equal to 5. And so we have this y double prime is equal to negative 2x, and we replaced the x cubed plus y cubed with the number 5. And now we have 2x times 5, which is 10x, and now this second derivative, which originally looked complicated, actually simplifies very nicely into negative 10x over y to the 5. Okay, I think you're ready to tackle some of the classwork, and good luck.